All right. Again, this is actually the third video of this section that has nothing new. It's just more problems. Let's do some problems directly pulled from the textbook homework assignment, starting from 315. Just give you some more practice. Again, don't watch all of these at once, but pick and choose. Try to do them out beforehand is a good idea. And then you can look at the video to see where you went wrong or see how to approach it. To carry a suit on an airplane, a suitcase on an airplane, the length and the width and the height together must be less than or equal to 62 inches. Assuming the base of the suitcase is square, and I guess we're assuming that it's... All right, so it gives us the volume equation already. The volume of equation is h times 31 minus 1/2 h squared. Like so. What height allows you to have the largest volume? You want to maximize this? And there's a lot of information here that we're not explicitly using. We're implicitly using it. The length plus the height plus the width of the box must be less than or equal to 62 inches. The base is square. Oh, it wants us to show that that's the volume. All right, so it wants us to show where that comes from. So we are using everything. So we're assuming that we have a rectangular base suitcase. Sorry, a square base suitcase of any variable we want. Call it X. It does want the height to be labeled H. We know that the volume of this is the area of the base times the height. And we know that if we add all of the length and width and height of the box, it has to be less than or equal to 62. So 2x plus h is less than or equal to 62. And if we want to maximize it, let's just say, whoa, that was too big. If we want to maximize it, let's just say it equals 62. Because we want to maximize it. So, in order to solve this problem, we want to substitute out one of these variables so we can use calculus. So h is 62 minus 2x. But that's what I would normally do. That's what I would normally do. But the problem is wanting us to show where this comes from. It wants in it, why I'm doing this whole problem in green, apparently. It wants us to show where this is coming from. I usually switch colors. So they solved for x. They got rid of an x. So we can do that too. 2x is 62 minus h. X, divide everything by 2. So the volume is x, which is 31 minus 1/2 h squared times h. Yeah, that's exactly what they got. So that was the first part of the problem. Show that that is indeed the volume equation. And the second is just finding the maximum. What's our domain here? Well, the smallest that h can be is 0. What's the biggest h can be? I think it's 62, right? I have to think about it. Because the biggest h can be has to do with our constraint. And yeah, if x is 0, h can be up to 62. We could have a 5-foot tall suitcase that's infinitely thin. Apparently, according to this airline regulation. I don't believe that. But whatever, it's a simplified problem. So the maximum of this volume will either occur on the endpoints, when the height is 0, when the height is 62, or at the critical points, which we're going to have to solve for. And again, the volume at these endpoints is 0. It is either infinitely tiny and very wide, or infinitely short, or very tall and infinitely tiny in that direction as well. Again, these are the independent variable and the dependent variable. So height of 0 is a volume of 0. Height of 62 is also a volume of 0. Find the maximum. Let's look at the critical points. And you can either use the product rule here, or you can FOIL it out first. Do you want harder calculus or do you want harder algebra? I'm going to choose the algebra. Let's foil it. I don't want to foil this out. I'm going to do the harder calculus. These are big numbers. I'm going to have to type in 31 squared into my calculator. You can do either way. So if we use a product rule, derivative, this will be our f, and this will be our g. Derivative of the first thing is 1 times the original second thing. Oh, we're gonna have to FOIL this out anyway. And then plus the first thing times the derivative of the second thing. We made the wrong decision, but I'm sticking with it. So use the power rule and then use the chain rule. Derivative of the inside is -1/2. This is v prime. Simplify v prime. It's going to be 31 minus 1/2 h. Whoa, the squared is not on the inside. You can't come in. And then the 2 and 2 cancel. We have a negative. Yeah, I definitely made the wrong decision. -h times 31 minus 1/2 h. Actually, no, this works. This works. This has a different solution than I was expecting, but it works. We need to find all critical points, so that's when this derivative equals 0 or when it's undefined. It's defined everywhere. To find when it equals 0, we can either FOIL and distribute it out or factor everything. So if we factor it, we get a 31 minus 1/2 h, and then we're left with a 31 minus 1/2 h from the first term when we factor out one of them, and we're only left with a minus h on the second term. Ah, this actually worked out nicer. I did make the right choice. So we have a factored equation equal to 0. That's true in each individual piece equals 0. So in 31 minus 1/2 h equals 0. And in the other piece, which is 31 minus 3/2 h, equals to 0. It's going to be when h is 62. We don't care about that one. We already talked about that one. And when h is equal to 2/3 of 31. That's 62/3. What's that? What is that as a mixed number? 20 and 2/3? I almost never use mixed numbers, but it makes sense when talking about the dimensions of a box, of a suitcase, I think. All right, all that's left is finding out what the base has to be. What is x? That's where we'll finish. So x is 31 minus 1/2 times h, which is 62/3. That's 31 minus 31/3. That's 93/3 minus 31/3. That is 62/3. Really, all of that, it's the same answer. So the base and the height are the same. A cube. It kind of makes sense, I guess, that it would be a cube. All right, that should be our answer. I don't want to go on the next page, so I'm just going to say the dimensions that make this work are 20 and 2/3 inches in all dimensions. And again, as a quick reminder, you can graph this on Desmos to check your answer, or there are answers in the back of the book to odd problems. We're doing 315. 315, the answer is a height of 62/3 inches. It only asked for the height. It didn't ask for all the dimensions. I'm not reading any of the problems today. I'm tired. You may have noticed this. There's been a lot of videos in this section. You may or may not have noticed. I also had another video that I trashed because I didn't like the way I was doing it. Let's do another one. Well, here, let's color code all these problems. Let's do one in blue. 330. Consider a limousine that gets this gas mileage. M of V equals 120 minus 2V over 5 miles per gallon. Who writes miles per gallon that way? Don't we usually write mpg? At speed v in miles per hour. The chauffeur also costs $15 per hour. I don't know how to spell that word. Is it like this? No. Close. Does it really have 2 U's? I don't believe that. I don't believe that. Chauffeur. All right, whatever it does. It's $15 per hour. And gas is, we should update this. Gas is $7 million per gallon. Let's say it's 3.5 for the purpose of the problem. Dollars per gallon. And yeah, this is, this is true. You do have different your gas mileage is different depending on how fast you're going. There's a sweet spot for every car for getting to a location with a minimum cost of gas. But here we're also paying for a chauffeur because we have a limo. I've never rented a limo before. I don't really know how it works. But find the cost per mile at speed V. So we're not optimizing in 330. That's 331. That one's for you guys to do, but I'll help you set it up. The cost per mile. Well, the cost is going to be the cost of gas plus the cost of the chauffeur. It's a weird word. Is that French? Probably French. So what's the cost of the gas? The cost of the gas is, well, what's your miles per gallon? And what's your gallons? I guess we're not doing a distance here. We're doing cost per mile. Cost per mile. So let's go off to the side real quick and type that. The cost of gas, the dollars of gas per mile, the unit should work out. So miles per gallon. Wait, I'm totally blanking. It's definitely $3.5 per gallon. We're going to start with that. $3.5 per gallon. And then we just have to make sure the units, we already have the dollars, but we have miles in the bottom, or we have gallons in the bottom when we want miles. Do we really want the cost per mile? I guess we do. Huh. Then we have miles per gallon, but I think we want the reciprocal of this. So we want, right? In order to get what we want, we need gallons on the top and miles on the bottom, because then the gallons are going to cancel, right? Wait, this problem is trickier than I thought. I'm glad I'm doing it for you. Because I do look through the problems to decide what things I want to give you a little help on. Yeah, so this is what we need. But the function on the top, that function on the top gives us the equation for miles per gallon. But to get the dollars in gas every mile, the cost per gas per mile, we need it in the right form. So in the top is miles per gallon. We want gallons per mile. Well, miles per gallon and gallons per mile are just reciprocals for each other. It's going to be 5 over 120 minus 2V. Huh. Interesting. I'm not sure if this is right. So the cost of gas per mile, according to this, is 3.5 times 5, $17.5, divided by 120 minus 2V, plus the cost of the chauffeur every mile. So the cost of the chauffeur is $15 every hour. So again, we're curious about the dollars for the chauffeur every hour. And we know the chauffeur himself or themselves is $15 every hour. Sorry, we want the cost per mile. Right? That's what we want. We want the cost per mile. And this stuff over here on the right is especially what I want to show. So even though the problem has a silly function, I still think it's worth doing and still good practice. And that's why I want to show here instead of just tossing it. So we need to kind of convert what's the relationship between those hours and those dollars? Well, the hours and the mile. Well, it has to do with the velocity, right? We always move V. We're going V miles every 1 hour. So 1 hour takes V miles. V miles per hour. Right? If you're going 60 miles an hour, how far do you go in 1 hour? 60 miles. That's that V would be that 60 in that case. Okay, so that's what we do to get that second cost. So it's going to be plus 15, and again, the hours cancel, $15 divided by V. So I guess that's where it kind of takes into account if V is 0, the cost is still infinite because we never get there. So I guess it's taken into account in the other place as opposed to here. So this is our cost function. Cost function, C of V in dollars per mile. V in miles per hour. That is the answer to 330. And in 331, you can find the maximum. And again, your domain in this function, V goes on the interval from 0. 0 can't be included here because that would cause us to divide by 0. And the biggest we can get is 60. And that's a little unclear where that 60 comes from, but it has to do with this guy right here. If V is 60, then again, the cost shoots to the roof again. This limo is just going, this problem could be fixed very easily by saying this model is only valid for certain speeds. But so this is your interval that you'll do for the next problem for 331. Actually, yeah, not as garbage of a problem as I thought. It just needs a couple of quick small fixes. But that's how you do 330. Do 347 next. Let's not do it in red. It's a bit hard to see. I like having fun with colors, but I need to make sure it's still readable. Consider the points on the given graphs and use a calculator to graph the functions. Where's the line y equals 5 minus 2x closest to the origin? Y equals 5 minus 2x. Oh, we might need a reset. Let's go from -5 to 5. Where is this line closest to the origin? Where is it closest to the point 0, 0? 0, 0, not 0.0. Well, any point on this line is an x, y, and we know the y coordinate, and we're trying to minimize the distance to the origin, right? We're trying to minimize the distance from point xy to the origin, distance from xy to the origin, and we know that y is equal to 5 minus 2x. So what's the distance? The distance is the square root of x minus 0 squared plus y minus 0 squared. Remember your distance formula, any 2 points. So we can simplify this, right? Square root of x squared plus y squared. And we know what y is. So square root of x squared plus 5 minus 2x. squared. Minimize this distance. What's our domain? X can be anything. X is in the interval from negative infinity to positive infinity. So to make sure that there is a minimum, we have to look at the limits. This is a continuous function. And it's defined everywhere. So the limit as x goes to the left of this function, well, that just becomes infinitely big plus infinitely big. The square root of infinitely big is infinite. And the same logic for negative, because we're getting squared. Everything's always going to be positive. So there is no absolute maximum. Remember 4.3, but there is an absolute minimum, and that's going to be at the critical point. So take the derivative. D prime, let's rewrite this first. This is going to be interesting. X squared plus, let's FOIL this out. 25 minus 20x, when you FOIL it out, plus 4x squared, all raised to the 1/2, and simplify the inside. It's going to be 5x squared minus 20x plus 25. You could take out a 5, but it's not going to help us yet. So take the derivative with respect to x, use the power rule and the chain rule. We're going to leave the inside the same, subtract an exponent, and multiply by the derivative of the inside, 10x minus 20. Let's find the critical points of this guy. Well, the critical points of the original function using this guy. So let's rewrite this. So on the top, we can factor it. Let's I don't know if I want to factor it. Let's not factor it. We don't have to simplify. 10x minus 20 over 2 times the square root, 5x squared minus 20x plus 25. We want to find when is this undefined and when is this equal to 0. So it's undefined when this denominator equals 0. And again, if you just want to check, because my gut says this is never going to happen, if you want to check whether that has any solutions, just look at the discriminant, b squared minus 4ac. b squared minus 4ac, it's going to be 400 minus 500. Yeah, it's negative. So it's going to be defined everywhere. That denominator is never equal to 0. So we just have to figure out when this is equal to 0, multiply both sides by the LCD. A fraction equals 0 only when the numerator equals 0. You can also do that by multiplying by the LCD. 10x equals 20, x equals 2. That's our other candidate. Well, it's not a closed and bounded interval. This is just our answer. When x is 2, what's the distance? Plug it into our distance function. This was our distance function. 5x squared, sorry, the square root. D was a function of x. It's the square root of 5x squared minus 20x plus 25. So the green is the line, and at any x coordinate on the line, the distance is the orange. So it's going to be this x coordinate when x is equal to 2. Really? Okay. So what is it asking? What is the problem asking us to find? Oh, I know why I'm surprised about that answer, and I'll talk about that in a second. It's closest to the origin at the point x equals 2, and the distance is about 2.236. But the y coordinate is also what we care about. And y is 5 minus 2x. The y equals 1. So even though We have an xd coordinate here, x in the distance. Our answer is at the point x comma y, 2 comma 1. And the shortest distance between a point and a line is done perpendicular to the line. So that's why I was surprised that this was the answer, because this didn't look perpendicular. But notice our scale is not, like, we don't have an actual, like, square boxes here. So if the step is 1, these should be squares. So like, it needs to be squares. So see how now the grid is squares. So now the point 2 comma 1 should look perpendicular. Like if we go straight between the point 2 comma 1, it should be perpendicular to the line. And indeed the line, the slope of the line is 2. So perpendicular, sorry, the slope is negative 2. So perpendicular, the slope is going to be negative 1/2. And yeah, negative 1/2 does connect these 2 points. Okay, that's how you do that kind of problem. Last one's 351. Last one I want to do for all of you. We have done a ton of problems here. Hopefully that's helpful. Set up, but don't evaluate each optimization problem. Also, if you're wondering why I haven't gotten rid of this, it's because a lot of times when I click the update button, it doesn't go away. All right, this time it did go away, so hooray. But the other day I was clicking it like 20 times and it just wouldn't go away. So set it up, but don't solve the optimization problem. We have a window. That semicircle in the picture is on top of a rectangle. We have 20 feet of window framing for the outer frame. What's the maximum size of the window that we can represent? So it says outer frame. Does that include this? I would imagine so. We want to maximize the size of the window. So this is what we have. And the radius is r. I think that's the only thing too important. 20 feet of window framing. We want to maximize the area of the window. So what is this area? Just the area of the rectangle, which is a base of 2r, times the height, which we don't know. That's the base, that's the area of the rectangle. And the area of the semicircle is 1/2 the area of the circle. 1/2 the area of the circle is 1/2 pi times the radius squared. This is the function that we want to maximize. And again, h and r need to both be positive. We'll have a greater than or equal to 0 for now. We'll see how that affects things different on. But we only have 20 feet total. So that the total sum of those lines needs to be 20 feet. So the boundary of the rectangle, which is the bottom plus the top, plus 2 of the sides of the rectangle, plus the top of the semicircle, which is 1/2 of the circumference. 1/2 of the circumference, 1/2 2 pi r. Adding up all of these needs to be 20 feet. Again, let me just make sure. 2r plus 2r is 4r, plus h is 2h. And then half the circumference of a circle of radius r is 1/2 of 2 pi r. So our objective function is up there at the top. Our constraint is this, 4r plus 2h plus pi r. It's easiest to solve for h here. So 2h is 20 minus 4r minus pi r. H is 10 minus 2r minus 1/2 pi r. Substitute that back into our area function. Area is 2rh which is 10 minus 2r minus 1/2 pi r plus 1/2 pi times the radius squared. And you could simplify this a little bit, and they probably do. Distribute 20r minus 4r squared minus pi r squared plus 1/2 pi r squared, where area equals 20r minus 4r squared minus pi r squared plus 1/2 pi r squared is going to be minus 1/2 pi r squared. So r is bigger than 0, but since h has to be bigger than 0, that gives us an upper bound on r as well. Right? When is h equal to 0? You could calculate it to get the upper bound, and I think we have to here. When h is equal to 0, that's our upper bound here. So in 10 minus, let's factor an r out here to get 2 plus pi over 2. So r times 2 plus pi over 2 equals 10. R is 10 over 2 plus pi over 2, which is about something. About 2.8. If the radius is 2.8 feet, that's basically the whole window. Okay. Let's check our answer. And again, the book really might have interpreted this problem a little bit differently than I did. 351. Area equals 20r minus 2r squared. Minus, yeah, so it's a little different. I have a 4r squared instead of a 2r squared. I'm off by a doubled factor right here. Where is that coming from? It's coming from my h substitution. It's coming from here. Oh, so yeah, so they're not counting. They're not counting here. So when they said outer, they didn't mean this. They meant just the outer. And I know they said the word outer, but yeah, all right. I don't know. It's really kind of weird to actually interpret, because actually they don't want this middle part at all, but it kind of looks like you'd need the middle part twice, which is not even what I was doing. So it just depends on the interpretation of the problem. But that's the process anyway. And that's what they want you to do. Yeah, they just wanted the outer here. If there's anything like that, I'll try to be very clear on the quiz. Okay. Let me know if you have any questions. Good luck with the assignment. There's a lot of problems here. They take a lot of time, but they're all pretty similar. Just sometimes it takes a little bit of effort, especially like in problems like that gas one or the swimming, running one, to get it formulated in the right way. But once you solve it, or once you formulate it, solving it is mostly just the calculus and just taking derivatives and doing some algebra. So let me know if you have questions, and have a good one. This is the second to the last section, so shed a little tear. You only got one more day of this after this.